Hello, everyone. Welcome back to class. We are going to continue where we left off in chapter 4. So today we should finish chapter 4, and next week we will start chapter 5. And it looks like I think I will be we will be holding our first quiz of the course. So I think it will be next Thursday on October, let's see here on our calendar. So October 29th. So I'll give all the details in an announcement, but basically we will meet on Zoom. You will have your cameras on, and before we begin, I will tell everyone, to do a quick sweep of their desk. Make sure they only have a pencil and the quiz itself. And how we'll do this is you'll simply either, print out the quiz and write on it, then take a picture of it and upload it to Canvas, or you can have a separate sheet of paper with you and view the quiz on your computer, and then you will submit that online instead. So take a picture of that or scan it as a PDF, whichever is easier. Just make sure the answers are readable, and if they're not readable, unfortunately, we cannot allow resubmissions if it's not readable. But anyway, the first quiz will cover chapters 1 to 4. I think that's a pretty good chunk of information to quiz the class on. So, in every course, there has to be quizzes and exams to test your understanding, knowledge, and that's how you earn your grade, and it's how we demonstrate merit in your coursework. So I might post a practice quiz. It might be two broken up quizzes that comprise chapters 1 to 4, but we'll see. I might have time to whip something up. So expect a practice quiz sometime over the weekend. I'll have to remind myself about that. But hopefully I will have time to do that. Otherwise, I'll just post 2 short quizzes that I did last year, and they should cover the same amount of information you can expect on the quiz on next Thursday. So the quiz will be focused on, I said chapters 1 to 4. So, I wanted to say about the length. So length will probably be 30 minutes. So it'll be 30 minutes. We'll meet on Thursday for 30 minutes. And then I will have a lecture prepared. It'll probably be the rest of chapter 5. So that'll be uploaded probably before the quiz. So you have time to watch that after the quiz or whenever you have time. But with that out of the way, hopefully everyone completed the chapter 3 homework. Chapter 4 homework is due next Tuesday, so don't put it off. I'm not putting it due Thursday because you probably want to be studying for the quiz. So chapter 4 will still be due next Tuesday at 11 p.m. So you'll have the weekend to focus on the homework, and that will prepare you for maybe 1 or 2 of the questions you can expect relating to the gas laws or maybe pressure conversions. I haven't decided yet. Okay, so let's get back into chapter 4. So we were talking about last time we were talking about Charles' law. So Charles' law is the relationship of gases. If you have a constant pressure and you change the volume or a temperature of a gas, the relationship is that volume is proportional to temperature. So as you increase the volume, you should see an increase in temperature. And likewise, the opposite, if you say you decrease the temperature, you should see a decrease in the volume of the gas that it occupies. So schematically, we could represent this as like so. So say we have a gas tube here, like so. And say right here is my thermometer. So I'm gonna make another little tube.
Your Google Home isn't set up yet. To get started, download the Google Home app on a phone or tablet.
All right, okay, like this, so a thermometer, like so. So this is my thermometer. Okay, so now just imagine this is attached by a rubber band. So this is like a rubber band here. And so what we call this tube here is like a capillary tube. So a very small tube, so capillary. And in here we're going to have a mercury plug. So right here is going to be my mercury plug, and I will color that gray. So let's make that gray like this. So here's my mercury plug. So the mercury plug is to show us that how the volume changes, because that plug will move as we raise the temperature. All right. So here's my mercury plug. And now, so let's make this a little bit, no, this is okay. So this will be, say this is the height of my gas right here. To the bottom here, this is my height. So and this is my height. So in this case, we can say at this stage that the forces, so let's say F is for forces, the forces pushing up against the plug is going to be equal to the forces pushing down on the plug. That's why the mercury plug, the forces being like the air pressure, the gas pressure. So the at equilibrium, right, or at a certain temperature, you'll have equilibrium, and that's where the forces acting pushing on the bottom of the plug is going to be equated to the forces pushing down on the plug. And those forces are due to the air particles. Okay. So what if we have, so as we increase the temperature, so say we have another diagram here where it's going to be at a certain new temperature. So say like, let's say our temperature right here is like at this stage. So our temperature is at here. So this red level represents our temperature. So now let's draw another tube here. So say we have, so let's just draw the scale first. So it's very, so you can compare it. So I'm going to try to draw this as equally as I can right here. Let me see. Yes, okay. All right, so here's my second figure here. So we're going to draw another thermometer here. Like so, and here's my rubber band again. And then now let's say the plug is going to slowly rise. So say the plug is going to slowly rise. So say my plug is right here, right? So now it's going to slowly rise as we increase the temperature. Okay, so see how it's slowly rising, and our temperature now is going to go up considerably, like so. So now we see that our height here is no longer the same, right? So this height, so say this is A and this is B. So height B is not going to be equal now to A. And in fact, our forces are not going to be the same, right? Because the forces acting upon the bottom of, say we heat the capillary tube from the bottom, right? So it's going to heat the gas particles at the bottom of the tube, and that will cause the gas particles pressure to increase, and that will move this here to kind of balance out the total pressure acting on the total pressure acting on the mercury plug. So in this case, the pressure is constant because we don't actually apply a stronger pressure. We're just modulating the current pressure so that the pressures above and below the mercury plug, the total pressure stays the same. But the pressure beneath the plug is going to increase because we're heating the gas sample. So as that rises, what we can say is that the force acting to push up on the plug, so the forces acting in the upward direction are going to be greater than the forces in the acting on the top of the plug pushing it down. That's why we see it slowly rise, and eventually we get to a situation C where again we have our plug here. Our capillary here. And we raise the temperature like so. So this is just representing the same kind of temperature in situation B. What we get at is a situation where now the height the plug is going to reach a stage where it's now in equilibrium at that new temperature. So say like right here. So now we can see from B, as we heat the gas sample, the plug will rise. Then once we stop heating at a certain temperature, that plug will stay at that temperature, will be balanced out by the forces again because it's open to the atmosphere. So the pressure will eventually equilibrate and stop rising because we stop increasing the temperature. So now we can say that this height C, this is height C, height. So that's the height of the gas. Oh, sorry, not there. Let me just backtrack. Sorry, guys. This is why we need to teach in class so you can catch my mistakes if I do make them, which happens from time to time. So now the new height is at that new temperature. Now the forces acting above, acting in the forward direction or pushing the plug upward, and the forces acting downward from the atmosphere pushing down the plug are now equal, and we're at now a equilibrium state where the gas plug will now be at its new position. Okay, so you can see from A, as we go to C, if we increase the temperature, the volume, the space occupied the gas will increase, resulting in the plug being pushed forward, upward to capillary tube. So this is the particulate view of Charles' law. So a good representation of what's happening on the plug is this. So say I'm looking at one of these at the blue areas above and below the plug. What we have is so in this situation we have, so here is, so no on a pencil. So say we have schematic here. No, this is great. So the gray particles will look like this. So this is from the bottom. So this is the bottom example. where we have a bunch of gray atoms representing the plug. And what's going to happen is that some gas particles are going to collide. So this is labeled as blue, and it's going to hit the surface of the plug and be reflected backwards. And we're going to say that at the bottom here, the forces are not equal. So the forces are not equal to the force acting above it. So this is the bottom of the plug. And then at the top here, we have F. So we say that the forces are not equal to from the bottom of the plug and the top of the plug. That's why the plug is moving upwards. So here we have, now from the top view, we see that the top view, we're going to see the particles like this on the bottom. We're taking like a slice of the plug and viewing the intersection. And now the blue particles will look like this, bouncing off, then bouncing out, away from bouncing and hitting the surface, causing a pressure, right? And we say that they're not equal, and this is the top of the plug. Okay, guys, so that's a particular view of Charles law. Now we'll talk about what this means mathematically. So we already shown graphically what it looks like. The graph, remember the graph looks something like this: volume, temperature, and we get a straight line out of the graph. So it means so we can say for the relationship between these two variables, volume is proportional to temperature. So what we want to say is that volume of a fixed amount of gas at constant pressure is directly proportional to absolute temperature. So if my volume increases, I should see an increase in temperature. Likewise, if I increase my temperature, I should increase in volume. But how you would see that change is that well, you could say it both ways. Increase in volume, then you should get an increase in temperature. Increase in temperature, you should see an increase in volume. So for the type of questions you'll see like initial volumes or temperature, and then you'll see a final volume or temperature, or not both, and you're asked to solve either for final temperature, final volume, or it could be reversed, initial volume or initial temperature. So that's a kind of example, a word problem that you'll be expected to do. Okay. So so we could take this proportionality and actually we can let's see here. So we can take rearrange this equation. We could convert this to an equation. So they do talk about proportionality constants, but that's not really well, okay, I won't say that. All right, let's just we'll go over this part. So when we're talking about proportionalities, so usually when we're talking about something's proportional to something else, they if they're directly proportional, they one must increase and the other variable must increase. So what we can say about volume is that volume equals a constant times T. So we add a constant because the relationship are related to these constants. So if I raise the volume and my temperature also raised because the ratio of my volume and temperature should always be the same if they're directly proportional. So that's how proportions work. So in this case, we can say constant times T. Then we could rearrange to solve for the constant. Constant equals V over T. So when we have one pair of volume and quantities, we can say constant equals V1 over T1. Now we get into the important part of the equation. So for a different set of volume and temperature conditions for the same fixed amount of gas at constant pressure, we can say that there's going to be another constant equals V2 over T2. So now that we have these two expressions, we can actually equate them to each other, right? Since they're both equal to a constant. Like the constant means that their ratios, their ratio will be one value. So whenever I increase one of them, then for my equation to stay the same, another must increase. So we can do this for different sets of initial volumes and temperatures and final volumes and temperatures. So what we can say is that V1 over T1 equals constant. And that will equal to V2 over T2. So, or we don't even need this constant anymore. So we can say V1 over T1 equals V2 over T2. So say I have a value for V1. Say the value for V1 is 5. So let's say V1 equals 5 and T1, I don't know, equals 1. All right. So now if we plug this in, we have 5 over 1 equals V2 over T2. Okay. So now let's say now we have a volume at, say, don't worry about units, say it's at 5, and now we decreased our volume to 1. Okay. So now we have 5 over 1 equals 1 over T2. So now we need to solve for T2. Okay, so what must T2 be to satisfy this equation, right? So since we have 5 over 1, then we decrease the volume. Now it's 1 on the numerator. So now T2 must also decrease, right? To ensure that this fraction, or to ensure that both sides have the same value, because they're directly proportional. So if you increase 1, the other factor must also increase to keep the proportion the same on both sides. Okay, so if you can do this math in your head, that's great, but I'm not expecting you guys to do that. So let's just solve it. So times type T2 by both sides, and we get 5 times T2. 5 divided by 1 is 1, right? Then we get 1. So T2, divide both sides by 5. Oops, can't draw 5s. Now we see that T2 is 1/5. So if I decrease my volume by a factor of 5, so I went from 5 to now 1, then my temperature should also decrease by a factor of 5. So in this case, if my temperature is like what, 1, and I decreased it to the volume by a factor of 5, then that must also be decreased by a factor of 5. So we get 1/5. Excuse me, guys. Sorry. So that is how Charles' law works. We express our volume, the relationship, as a constant times temperature. You can also do it the other way around. Temperature equals volume times constant. It doesn't matter. It will because you can also rearrange it as T over V, but I wouldn't do that. Just follow what I've shown you here. If those of you are curious about that, you can also rearrange it the same way. I have tested that before. So the reason we add a constant is because we want to change it to an equation to be able to solve for variables when we're given a word problem, and we'll go over that in the next slide. So let's look at the next slide. And I was right. Let's put this into practice. Okay. So I just want to make sure we so let's just jot this down. Convert proportion to an equation by adding a constant. Okay. All right. So let's go to our first active exercise for today. So here's active exercise. All right. So here we have a container with flexible walls. Holds a gas that is cooled. From 65 degrees C to 22 degrees C with no change in pressure. So I know this might sound kind of funny, because how does if you decrease the temperature, how does that not result in a change in pressure? What we mean by change in pressure is the mean in total pressure of the system. So even if you decrease the pressure like on one side of the system, the other side of the system will increase. Will probably increase, and that will make up for the total pressure staying the same. So for these cases, when we say constant pressure, we mean no change in the total pressure of the system. So what I mean by the other side is the surroundings. So the pressure from the surroundings or the atmosphere. Right. So that is what we mean by no change in pressure. So if you're having trouble visually thinking about that, I would consider thinking about the system itself. Like you have the surroundings, and you have your system that you're looking at, the gas itself that's being heated. Okay. So all right. So the things we want to note is if the container volume was 4.5 liters initially, what is its volume after being cooled? All right. So something. So I know this is a lot of words to consider, but you just need to break it down piece by piece. So let's talk about what we're given. So here is our given. We're given 4.5 liters. That is our initial volume. So we're going to denote that as V1 in our equation that we just went over. And we also have 65 degrees, and that is our initial Celsius temperature. So that is our T1. And next we have 22 degrees Celsius, or our final Celsius temperature. T2. So what we want is, what's wanted is final volume and we're going to assume that we're going to solve for liters. So our final volume is going to be in liters. So we're looking for V2. Okay, so what you should always do is write the equation you want to use. So notice that there's no change in pressure, right? So use the equation that has no P in it. We'll be going over at least two more gas law equations, and don't worry. On the quiz, you're able to use like a conversion sheet, and I'll put the gas equations on there for you to use. So you don't have to like remember explicitly these equations, but you need to know how to manipulate the equation and solve for variables. So that will not be provided on the quiz. You'll have to do that by showing your work. Okay, so we have V1 over T1 equals V2 over T2, like so. So let's say we're solving for V2, right? So we're going to multiply both sides by T2. T2's cancel, and then we have T2 times V1 over T1. So our volume equation simplifies to T2 over T1 times V1. So it may be helpful to separate out the fractions by variables. So maybe it's, I don't know, less confusing. So we're going to be multiplying our first volume by a factor of the two temperatures, because the the temperature units will cancel out, right? So here's so one of the most common mistakes is people forget to convert Celsius to kelvins. So we need to convert Celsius to kelvins. So first we want to set up our, put in our units. So V2 equals 4.5 liters over 65 plus 2. So let's just do it this way. So 4.5 liters. I'm just going to do it this way just to make sure it's consistent. So our first temperature was our T2 is now 22 degrees Celsius. So we're going to be 22 plus 273. Don't worry about the extra digits. Just keep 273. That's perfectly fine. So that's Kelvin. And then we're going to have 65 plus 273 kelvins, like so. So our kelvins cancel, and then we're going to multiply that ratio to our volume, which is 4.5 liters. So notice that we're going from a higher temperature to a lower temperature. So we're going to get a fraction as our factor, and when we multiply that by the volume, our volume should decrease. And what we should get at the end is 3.9 liters. So let's check that our temperature decreases, which leads to decreased volume. So my answer sounds okay. And my temperature fraction is going to be less than 1. So we're multiplying by our volume to a smaller number, which is 3.9. Okay. Hopefully that was okay, guys. Just some tips. Remember to convert temperature to kelvins. That's one common mistake that will cost you some points on the quiz. So don't make that mistake. So the typical problem is a word problem. You show your work. I'll ask you to solve for one of the variables, and you should be able to set up the equation, show your work, and get the final answer. So never do these questions, these problems like mentally in your calculator, and just write the final answer. You will lose a bunch of points for that. So even though you have the right answer, that's not always what's important. It's always what's important is to show me your thinking process and how you critically thought about how to approach the problem. So problem approach and problem solving is what's big in chemistry. Even you know the right answer, you can't show how you got there. There's really no merit in that. So always show your work, be proud of your work, and circle your final answer, and you'll get full points. Okay. So hopefully that was okay. You just followed how to do this example. You could tackle any of the problems I give you on the quiz. Okay, so next we're going to go into Boyle's law. Okay. So let me just check the time. 40 minutes. Okay, we should be okay. So Boyle's law. So Boyle's law is the relationship between pressure and volume. So there's a slide depicting pressure, Boyle's law. I encourage you guys to look at it. I'm not going to mention it much here because I could just explain it in words. So Boyle's law is when you increase the pressure of a gas, the volume should decrease. So for example, if I had I mentioned this a lot with the piston example. I could just show you this in the schematic here. So say I have a piston here. So at constant temperature, so say at constant temperature, the pressure of a gas is inversely proportional to the volume occupied by the gas. So if I have so say this is a piston, right? So this is a piston, metal piston, and here are my gas particles moving about. So they're going to be moving about like so. So this will have a pressure and volume associated with P1, V1. Now if I decrease the volume, say I decrease the volume. So right here I have my flask. Well, it's just like a tube. So now I decrease the volume of the gas. So now I'm going to make it a little bit lower here. So in this case, V2 is not equal, and this is V1. So V2 is now not equal, and now the gases will move much faster. It's very hard to scheme this, but just say that there's arrows of the gas particles moving faster. like so. So this, so when I decrease the pressure, I have, not pressure, decrease the volume, the gas particles now, in order to maintain that same relationship. Remember P2 V2. So to maintain that P2 V2 is equal to P1 V1, my pressure must increase if my volume decreases. And we can explain how this, why this occurs, because as we decrease the volume, the amount of space gets reduced that the gas can occupy. That means that there's less space for gas particles to move, and that'll mean they'll reach the size of the container much faster at constant temperature, and they'll also have more collisions. So the frequency at which they hit the walls at any given time will be increased relative to the original conditions where the volume was much bigger. So that's why as you decrease the volume, the frequency of collisions will increase of the gas particles, and that collision between the walls of the container will increase, or of the piston will increase the pressure. All right. And on figure 4.20, there is a good schematic of how we measure this. But the relationship here is we have a graph here. Here's my pressure. Here's my volume. And we say they are inversely proportional, like so. So as my volume increases, my pressure is going to go down, as I see from this graph. As I increase my volume, my pressure decreases. So that is Boyle's law. So this is Boyle's law. So these people are significant for our understanding of how gases behave. Okay. So let's talk about Boyle's law. So volume is inversely proportional to, it's proportional to this, 1 over pressure. So we say that this is an inverse relationship. Or we could say this. So when we compare this, when we translate this to an equation, we can say V equals constant times 1 over P. So we need a constant because it allows us to say that, oh, volume is this times the pressure. We need that constant because it allows us to go from just saying that it's proportional to saying that we cannot now use actual numbers, because that constant allows us to use equations. And you'll see constants pop up all the time when we're trying to use numbers to represent something. For example, like the speed of light. Yeah, we'll learn about gas constants. Also, there's also other constants too, like Planck's constant when we talk about energy levels, but those are just some example of where constants come into play, or that's how I see it. So V equals constant over 1 over P. Now we can solve for constant and we get P times V equals the constant. So see here, times P to both sides. And remember, constant times 1 is just the constant itself. So the constant, I wouldn't worry too much what it means. It's just like a number that we just multiply to kind of make these two variables equate to each other. So don't worry about what the constant or the number, what it means. Just know that we use it to get this equation. And at the end of the day, what we want to remember is that volume is inversely proportional to pressure, and that we can use this following equation to to solve for pressure and temperature. So then, like we did before, we said P1 or V1 equals constant, and we can also have another set of conditions where P2 times V2 is also constant. So another way of looking at constant means that it's this one number, and that P2 times V2 is also one number. So we can set these two equal to each other because these two equalities must be equal to each other. And that's what we mean by having two equations that are proportional using variables. So we could say P1 times V1 equals P2 times V2. So now if my pressure increases in one, then to kind of make sure that both sides are equal, my volume must decrease based on this multiplication here. Okay, so we'll go into example how this one works. So the takeaway is the constant you should think about is we use the constant to make sure that we can make these make an equation for pressure and volume and for volume and temperature in the previous law, and then we can set these two equal to each other because one set of temperature at one set of pressure and volume, we can equate that to another set of pressure and volume and solve for an unknown variable. And the constant allows us to do this, and that proportionality of pressure inversely proportional to volume, we can set them equal to each other and solve. So that's another reason why we need a constant, because it has a constant number, and then the other set of values will have a constant number. Then we can set them equal to each other. That's what makes it able to be we're able to set these two sets of variables or of pressure and volume. We're allowed to set them equal to each other and solve for an unknown essentially. So hopefully I kind of rambled a bit, but hopefully that wasn't too confusing. Just know that's how we get our gas equations. P1 times V1 equals P2 times V2. And that'll always be the same for the other gas laws. So the constant is merely just a way to set these equations up equal to each other. Okay. All right, let's try example here. So active exercise. So try these on your own first, and then come back and see how you did. So let's go with a gas sample. Occupies 5.18 liters at 776 torr. So I want you to find the volume of the gas, if the pressure is changed to 827 torr. One thing you also want to keep in mind, temperature. And amount remain constant. So you want to use the equation that does not have T in the equation and only has P and V. So now let's talk about how to solve this. So we're given, so you can also list what you're given if that makes it easier to digest what you just read. So given is 5.18 liters. So that is our initial volume. And then we have 776 torr. Initial pressure. So for pressure, you do not need to change units. The only unit you have to change is temperature if it's given in Celsius. So that's our initial pressure. So that'll be our P1 here. And then finally we have 827 torr, which is our final pressure. Pressure P2. Okay, and what we want is final volume. V2. So let's specify which equation we should use. We should use P1 times V1 equals P2 times V2. So just note that when I put, this is also equal to P1 V1 equals P2 V2. So when we stack together two variables, like X or Y, it's always a product. So it's always going to be P1 times V1. So for now, I'll for this example, I will show you how I multiply it like this. But in the future, when we talk about stuff like this, I'll probably leave it as P1 V1 equals P2 V2 as opposed to P1X V1 equals P2X V2. So just get the hang of that and just know that when two variables are next to each other, it's always multiplication. It's addition if there's a plus sign, and division if there's a division sign or a fraction, and subtraction if there's a minus sign. But when we're having them directly next to each other, that's another way of saying multiplication. Okay, so we're going to solve for V2. That's what we need. So we're going to divide both sides by P2. And so now what we have is V2 equals P1 over P2 times V1. Okay, so if you do have a two different pressure units, you will need to convert one to the other unit so you can keep it consistent, because this won't work if you have two different pressure units. Your answers will look wonky because they're two different units, so the scale is going to be, the scale between the two values is going to be different. So now let's solve, plug and chug, as they say. Now we have 5.18 liters. Since both of them are in torr, you do not need to change anything or convert. So 76 torr over 827 torr. So our torrs cancel, and we see that our pressure went from our pressure fraction is less than 1, so our volume should decrease, and that makes sense because our pressure increased from 776 torr to a final pressure of 827 torr. So our volume should decrease. So what we get is 4.86 liters. Okay. So just make sure that our pressure increased, so our volume should be smaller, and it is. So when for these types of questions, so always check that that your answer seems reasonable. Always double check if you have time. But what's important here is work. So if you just give me an answer and show no work, there's really no points I can give you if you're wrong. But if you're wrong, I can give you the points if your setup is correct and you made a calculation error. Or maybe if you flipped maybe one of the fractions, I can still give you some points for that. So partial credit is always what I try to do. It's why I try to avoid too many multiple choice questions. I don't think that's really a fair gauge of your understanding. So I always try to do most of my quizzes exams as like free response, fill in the blank, vocab, stuff like that. However, I will warn you that the final exam will probably be all multiple choice. So you must practice the concepts and the problems. So the quizzes, the midterm, and the homework will be great ways to do that. For homework, I always advise you to have a notepad, maybe your iPad or something, pencil, pen, and be ready to like take like do like calculations and show work. That's how you prepare yourself for the exams, so you get that practice on writing and showing your work. Okay. All right, guys. So we only have 6 slides left, so we should be able to make it. All right. So now we're going to talk about the combined gas law. So the combined gas law, so as it sounds, it's basically a summation of Boyle's and Charles's law. So now we combine the two proportionalities. So remember, Charles' law is this. V is proportional. So apparently I cannot write the proportional sign, but that's proportional. That does not mean alpha. So sorry if that's not clear. Like the Greek sign for alpha, that's not what I intended to do. So volume now is, so let's try to make it better. Yeah, they're so similar, right? They look kind of the same. So yeah, sorry for any confusion. Volume proportional inversely to pressure. So now we can combine the two and we can say volume is proportional. Man, that is bad. Maybe I should stop trying to do that. Proportional to temperature, which is proportional. Oh, so temperature times 1 over P. So it's proportional to temperature, which in turn is proportional to the times 1 over P. So now, like we did before, we insert proportionality constant. V equals constant times T times 1 over P. Like so. The reason we don't say temperature is proportional to 1 over P is because here we're just relating volume to the two other variables and not all three of them, because that would be confusing. So we have to look at one variable at a time. So the constant like so. So now we can solve for the constant, right? Multiplying both sides by P. So multiply both sides by P first. So we get P times V equals constant over T times T. Now we divide both sides by T. We get P times V over T equals constant. So now we can say that now that we know that there's a constant value for a given set of variables, we can equate a first set of variables to another set of variables. So remember we said that P1, V1, and T1 equals constant. Well, we can also say that another set of conditions are also equal to that constant, P2 times V2 over T2. Now we can say P1 over V1 over T1 equals P2 over times V2 over T2. So this is called the combined gas law. So what this states is that volume for a fixed quantity of gas is proportional to temperature. And inversely proportional proportional to pressure. That's just a summation of Boyle's and Charles's law. Okay. All right, now let's put the pieces together. Let's do an active exercise. So here's my active exercise. These are designed for you to put the concepts together and really make your learning experience as active as possible. So when I took classes, I try to be active as I can, but they were mainly in my chemistry courses because I found them the most interesting. But I found that learning from instructors who actually wrote stuff out, I actually clicked more for my brain. So I'm not sure if many people prefer that, but I absolutely disliked lecture slides because whenever, even if I read ahead, when the professor showed me slides, I really didn't retain anything he told me, and I would have to reread the slides, and then they're not fun to reread. So I don't think I was a very visual learner, I guess. But anyway, everyone's different, so I'm just trying new things. Last time I taught this course, I read off the slides, but we also took the time to do these active exercises, so I think that made the difference there. But this year, I'm trying a different approach. So we have a cylinder in an automobile. The engine has a volume of 352 centimeters cubed. So remember, that's a volume unit. This engine takes in air at 21 degrees Celsius and 0.945 atmosphere. Sorry, not atmosphere, ATM pressure. Well, it is atmosphere, but sorry about that. So what I want you to do is here, the compression stoke squeezes and heats this gas. Until the pressure is 4.95 ATMs. And the temperature is 95 degrees Celsius. Whoops. So our question is, what is the final volume of the cylinder? So another thing to keep in mind when doing these questions is just read through the question, find out what you need to know. Because sometimes when people approach problems like this, they don't really read the question, and then they put an answer that doesn't address the full question. So they lose points like that too. So one thing I would keep in mind is that, when, again, try to read through calmly the question, then jot down stuff first and what you need to find out. So when you go back, maybe to look for information, you know what you're looking for. But those are just my suggestions. So how we solve this? Given. What are we given? So list down what variables you know. 352 centimeters cubed. So that's my initial volume. So my initial volume is V1. Now 21 degrees Celsius. That is my initial temperature. Oh, sorry, guys. My initial temperature. Initial temperature, T1. Now I have 0.945 ATM. So of course you don't have to list it like this. You can just say, oh, T1 equals this, P1 equals this, and V1 equals this. That's probably a lot better in terms of time on the quiz, time management. But this is just for getting you in the hang of it for practice, so you know how to maybe list your information in a very organized manner. That will make finding your answer much easier. So initial pressure P1. Then we have 4.95 ATM. That is our final pressure. P2. And then 95 degrees Celsius is our final temperature. So T2. So what we wanted is final volume. So this one, it can get a lot of variables. So I encourage you to write down all the variables and their values. So we're going to use our equation P1 times V1 equals T2. Sorry, no, that's wrong. Don't get that mixed up. People get that mixed up too. P2, V2 over T2. Okay, so we cross multiply and we're solving for V2, right? So let's cross multiply here. So what cross multiply means is I take my T2 and multiply it that way, and I take my T1 and multiply it that way. So we get P1, V1, T2 equals P2, V2 times T1. Okay, so that's how we cross multiply. I mean, you could also do it stepwise, like multiply T2 first, then rewrite the equation, then multiply T1. But it doesn't matter. You'll get to the same equation here. P1 V1 T2 equals P2 V2 T1. All right, so now this just makes it easier to solve for V2. So we get V2 equals V1 times P1 over P2 times T2 over T1. Okay, so we came to this new equation by dividing both sides by P2 over T1. So this cancels, and we get P2 over T1 here. like so. Okay, so I just rearranged it like that to make sure everything is clear to see. Then we just plug and chug 352 centimeters cubed times. So they're in the same units, so no need to there's no need to convert anything. 4.95 ATM times. Now our temperature 21. Let's just make sure that our final temperature is T2. Okay, so our final temperature is 95, so that should be here. 95 plus 273 K over 21 plus 273 K. K's will cancel out. And then what we're left with is 84.1 centimeters cubed. So our volume decreased. Let's see if that makes sense. Our pressure went up to 4.95 ATM. So our volume should decrease. And our temperature, so what the temperature in this case, so our temperature of volume should decrease. So ignore that. So when so what we're looking, so this one here, you just need to look at the fractions if they make sense. So our pressure went up, right? So our volume should decrease, so that makes sense. Our fraction is less than 1. And then for our temperature, our fraction should be greater than 1, right? Because if our temperature increased, our volume theoretically should increase. But in this case, the fraction for the pressure is lower, so it overwhelms the temperature fraction. So it eventually decreases overall. So just make sure that your temperature fraction in relative to the volume, that it should be greater than 1. And then for your volume, it should be less than 1. Okay, so hopefully that was okay. So there is a typo in this on the lecture slides, so please refer back to what I have said on the video. Sorry about that. I forgot to fix them when I found this error last year. Sorry about that, guys. So, but if you catch that error, that's a good sign. Okay. Okay, so we have 6 minutes left. And we should be good. There's only 3 slides left. All right, guys, hang with me for a few more minutes. So let's talk about standard temperature and pressure. So you may have heard of STP. That's called standard temperature and pressure. That's a way for us to kind of talk about some quantities for relating to gases. So the conditions for standard temperature and pressure are conditions of temperature at 0 degrees C and a pressure of 1 bar. At which gas volumes and quantities are measured and compared. So it's always like a standard unit to compare all our gases, so that we know that 1 mole of its gas equals this much volume, stuff like that, and quantities, and or compared. Oh, sorry, that doesn't make sense. What I meant to say is are measured and or compared. Sorry, guys. Okay. So these are recommended by the International Union of Pure and Applied Chemistry, or IUPAC, but you guys don't need to worry about that. All right, let's talk. So this will be our last exercise. So let's talk about that. Okay. So guys, the volume of a sample of nitrogen gas is measured as 3.62 liters when it is at 0.843 bar and 16 degrees Celsius. So what I want to ask is, what is the STP volume of the nitrogen gas sample? So remember STP, so how we do this is, remember that STP is 0 degrees Celsius and 1 bar. So that gives you your final volume, pressure, and your final pressure and temperature. So we're given 3.62 liters as my initial volume. .843 bar. So that is my 8.43 bar. So that is my initial pressure. P1. Now 16 degrees C. That's my temperature, initial temperature. C1. Then we have 0 degrees C as my final temperature, because that is STP conditions. And lastly, we have 1 bar as my final pressure. 1 bar final pressure. So that is P2. Okay, so remember STP conditions is 0 degrees C and 1 bar right here. Okay, so now let's, so we're almost done, guys. This example, it will be the last thing we do, and maybe one comment. V1 times P1 over P2 times T2 over T1. So remember, this is from the combined gas law. So we get, so remember, we write out P1 over V1 over T1 equals P2 V2 over T2. And we can just solve for V2. We will get this equation like so. Okay, now let's plug everything in. 3.62 liters times 0.843 bar over 1 bar those will cancel out times 0. So this is T2 on the top here. 0 plus 273. Remember to always convert to kelvins. And then 16 plus 273 for my initial temperature. What we're left with is 288.88 liters, or not 288. That will be an example of a very suspicious answer, because it shouldn't be a very different number. Okay, let's check our values. So my volume decreased, right? So since my volume decreased, my pressure should have increased. And in this case, right. So my pressure, my pressure decreased. Sorry, not pressure. My volume decreased, right? So my fraction for the pressure should be less than 1, and it is. So that will give me a, will give me a smaller fraction. So my volume will decrease, right, when I multiply it. And so my temperature, I went from 16 to 0. So my volume and temperature, my volume should go down. So my fraction should be less than 1. And in fact, it is for the temperature. So that's a good check. So now we have 2.88 liters as our final answer. Let me just fix that here. So hopefully that was okay, guys. So always check your fractions that they make sense. For example, here, my volume decreased, so my pressure fraction should be less than 1, because my my P2 is large, should increase, and my temperature fraction should be less than 1 because my temperature decreased going to T2, so it should decrease. My volume should also decrease, and that checks out. Okay, guys, the last slide is just the last law, but we have no exercise for it. It's called, I know it as Gay-Lussac law. Gay-Lussac law. I don't know it as Hamilton's law. But it's rarely talked about because the combined gas law talks about it already. See here, P1 over T1 is proportional to P2 over T2, and that's similar to how we said V1 over T1 equals V2 over T2. So the combined gas law already talks about that proportionality. But in summary, it's P is proportional to T. And what it says is that the pressure, I'm just going to summarize it for you here. Pressure exerted by a fixed quantity of gas at constant volume is directly proportional. Oops. Directly proportional to absolute temperature. And conceptually, you can think about, if I raise the pressure, remember when we were talking about heating a gas will increase the pressure. or the frequency of the gas particles hitting and colliding with the surface of a container, that will increase the pressure. So as you increase the temperature, your pressure should increase. And as you decrease the temperature, your pressure should decrease because the speed of the molecules is decreasing. So the chance of it hitting the walls is going to be less frequent. So you get lower pressure. Okay, guys, that is chapter 4, all about gases. We'll probably won't revisit gases this quarter. So make sure you understand the properties of gases, how to use and apply the gas laws for solving word problems, and conceptually why the two variables are related, how they are: pressure and temperature, volume and temperature, and pressure and volume. So please not only know how to use it mathematically, but conceptually, like why should we expect something to decrease or increase for our final answer. But anyway, guys, I'll if there's any questions, office hours on Friday from 11 a.m. So if you need help with chapter 4, let me know. Or have any other questions, come by and visit. But there's with that, I'll see you guys next week, and we'll start chapter 5, which is, I think, one of the hardest chapters to conceptually understand, but I'll do my best. We'll be starting quantum mechanics. So we'll be looking at the nuclear model of the atom. All right, so we're going back to the very basics of the atom itself and what comprises it, and what does that tell us about how like these atoms or elements behave in chemical reactions. All right, guys, see ya.